Welcome to this lesson on carboxylic acids, one of the most important functional groups in organic chemistry. Carboxylic acids are organic compounds that contain the carboxyl functional group, represented by the formula -COOH. This functional group is responsible for the acidic properties of these compounds and makes them essential in both biological systems and industrial applications. Throughout this video, we'll explore the structure, properties, and reactions of carboxylic acids. The carboxyl group, written as -COOH, is actually a combination of two simpler functional groups. It consists of a carbonyl group, which is C equals O, and a hydroxyl group, which is -OH. These two groups are bonded to the same carbon atom. The unique combination of these two groups gives carboxylic acids their distinctive chemical properties. The carbonyl group makes the carbon atom electron efficient, while the hydroxyl group provides a hydrogen atom that can be easily donated, making these compounds acidic. Carboxylic acids follow a general molecular formula. The simplest way to represent them is R-COOH, where R represents any alkyl group or hydrogen atom attached to the carboxyl group. Alternatively, we can write the formula as CnH2n+1COOH, where N represents the number of carbon atoms in the alkyl chain. This formula helps us understand the pattern in the molecular composition of different carboxylic acids as the carbon chain length increases. Let's look at some common carboxylic acids you may already be familiar with. Formic acid, with the formula HCOOH, is found in ant venom and is the simplest carboxylic acid. Acetic acid, CH3COOH, is the main component of vinegar and gives it its characteristic sour taste. Citric acid, with the formula C6H8O7, is abundant in citrus fruits like lemons and oranges. Lactic acid, C3H6O3, is produced in mussels during exercise and is also responsible for the sour taste in fermented milk products. Carboxylic acids have three key properties that define their behavior. First, they exhibit acidic nature, meaning they can donate protons when dissolved in solution. This makes them react with bases to form salts. Second, they form strong hydrogen bonds due to the presence of both the carbonyl oxygen and the hydroxyl group. This hydrogen bonding results in relatively high boiling points and makes smaller carboxylic acids soluble in water. Third, they have a polar character because of the strong dipole created by the C equals O and O-H bonds, which influences their reactivity and solubility. Now let's understand why carboxylic acids are acidic. When a carboxylic acid dissolves in water, it can donate a proton, written as H+, from the hydroxyl group. The equation is RCOOH reversibly forms RCOO- plus H+. After losing the proton, what remains is called the carboxylate ion, RCOO-. This carboxylate ion is highly stable because the negative charge is delocalized between the two oxygen atoms through resonance. This resonance stabilization makes it easier for the carboxylic acid to donate the proton, which is why these compounds are acidic. Naming carboxylic acids follows a systematic pattern based on the number of carbon atoms in the molecule. A one-carbon carboxylic acid, HCOOH, is called methanoic acid. A two-carbon acid, CH3COOH, is called ethanoic acid. A three-carbon acid, C2H5COOH, is named propanoic acid. And a four-carbon acid, C3H7COOH, is called butanoic acid. Notice that the names are derived from the corresponding alkane names by replacing the E ending with OIC acid. These systematic names are used in formal chemistry, though many carboxylic acids also have common names like formic acid and acetic acid. Carboxylic acids participate in several important chemical reactions. First is salt formation, where carboxylic acids react with bases such as sodium hydroxide or potassium hydroxide to form carboxylate salts and water. Second is esterification, a reaction where carboxylic acids combine with alcohols in the presence of an acid catalyst to produce esters and water. Esters are important compounds with pleasant fragrances used in perfumes and flavorings. Third is reduction, where carboxylic acids can be reduced using strong reducing agents to form primary alcohols or, under specific conditions, aldehydes. These reactions make carboxylic acids versatile starting materials in organic synthesis.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.